All right. Let's begin. Born. You're trying to get a number. Have I got all the homework? It's not late. If you're back there copying off of somebody else, you better go ahead and hand yours in. But it's okay. He can copy it during the period, as long as you don't mind yours being late also. All right, born. I have a beam. Oh, that's ugly. Looks like it got caught in a wreck. And at point B, yeah, any place. No, I'm just going to be picking on people like Maley and Dismuke here. All right. That'll get some peace and quiet. And I'm going to put a load P at point B. Born. What is it going to do to that structure?
I'm going to pass that one on to Cven.
Fat chance. If you wait a half hour, you might. What will it do to that structure? It's going to bend it. You see, you thought you were ignorant. You really weren't. It's going to bend it. And it is going to cause a deflection at point B because someone loaded it at point B. This is point C. It is also going to cause some deflection at point C because someone loaded it at point B. Pick somebody at random here. Maley. How much how much work will be done on that beam? Force times deflection, I hear those numbers. It's a good start. Except the force starts off at 0, right? And it ends up at a full value P sub B. So it will be the average force through the distance. So the work done under this situation right here is going to equal to the average force times the distance through which that force traveled. Now then, I'm going to show you another beam. I'm sorry, is that a 0 or an egg? It's a 0. I'm sorry, did he say pancreas? I'm not getting the whole gist of things here. Straup? I don't know what to say, really. I mean, well, I'm just trying to take the average force. In other words, the force starts off at nothing, and it gets to be 1 kip, 2 kips, 8 kips, 30 kips, and then it reaches its peak value. And so the force acting on the structure started off here, and it got up to some value P, and it deflected it by some amount delta, and the work that you did on it is the area under the curve, average force times distance. So I'm saying started at 0, got this high, divided by 2. All right, here's a new beam. Incidentally, this force at P is still on there at point B. The beam still is deflected, but I want to show you only the new deflections that occur due to the new load that I'm going to add. I'm going to add a load at point C. And although, in other words, when the load C was put on there, it already looked like this. So the truth is that load goes right here. And it deflects the beam also. Now I'm only going to show you the added deflections due to this added load. This deflection right here is the deflection at C because someone put a load at point C. I need some way to identify these things. And under this load right here, it also caused some deflection. And let's call that deflection at B because somebody was tinkering around with loads at C. And in order to do that, if I told you to go push on this beam at this point, if it was a real beam and if it was 20 feet long, you'd say, I can't push on it, it won't move. I said, well, go get a hydraulic jack. And so you could push on it. The jack would start off with 0 force. At the end of it, it would say 100 kips, and your arm would be ready to fall off your body because you sat there and jacked that jack until it got 100 kips of force in it. Now then I'm telling you over here to go put a jack at point C, and I'm going to ask you how much work you have put into this system or how much work is done on the system because you caused these deflections. Booth? Sir. How about just this guy here? You're the guy with the jack. You're at point C. I want to know how much work you pumped on this thing to make it deform.
Out in the dark, same thing as the work above, except the C.
Okay, well, I'll admit there's some other people that are going to do some work on the beam, but just you, how hard did you start pushing? That's right. And how hard did you finish pushing? P sub C, divided by 2. And then you said times what? How far it traveled. So when you're out there with this hydraulic jack, a manual hydraulic jack, and you get this thing cranked down 1 inch and sweat's pouring off of you, and you come back in and you say, I think I'm finished. And I say, no, you're not finished. It's got to go down 3 inches. You got more work to do. But I will admit that this load having been set on the beam before we even got there, it also traveled through a deflection that just happened to crop up because you were pushing over here on this side of the beam. So there is some more work stored in the beam. How much?
PB divided by 2.
All right. All right. Now I understand why Booth said half of this force times the distance, but this thing was sitting here when you came and watched, right? And when you finished, how big was it? It's the same value. And therefore, that particular guy is not divided by a half. The work that's done on the beam, and of course that energy has to be stored inside of the beam, is strain energy and bending. That force is constant. So I'm going to add P sub B times the deflection at B because someone's been tinkering at C. And therefore the total work done on the beam is the sum of those two numbers. Now then I'm going to show you another beam.
Question.
Yes, sir.
Could you explain why you don't divide by 2?
Sure. You're this guy here with the hydraulic jack. You slip the hydraulic jack between the ceiling and the beam. You give it a couple of easy pumps and the little nozzle comes out the front end and it touches the beam. And all of a sudden things really start getting tough. And you're pumping and pumping and pumping just like you're raising a car with a flat, except you're pushing down. And it's pretty hard. Right now the force is 10 kips. And then, man, it's really hard because the force is 20 kips. And then it's really hard because the force is 30 kips. And when you get through, the force is 100 kips, or P sub B. It started at 0. It ended at this number. It started at 0. It ended at P sub B. And that means that the work done is not P sub B times delta. It's the average force times delta, because that's what work is. Integral, probably that's what I ought to say, is the area under that curve. It's equal to the integral of whatever the load is times delta. And then you integrate from 0 to delta, and that turns out to be the average force. Now then, this one, in answer to your question, is when you came in and rested this load on the beam, it did this to the beam. That thing is still sitting there in my world. I then went and I talked to Booth and I said, go get that hydraulic jack and bring it over here. And he says, oh, geez, man, you sure? Yeah, I'm sure. So he came over and he put the load on here. He started off with nothing. He went to 10, he went to 20, he went to 30, and therefore the work he did on the beam was equal to 1/2. You, on the other hand, that force that you had on there is just like a car. It's just sitting there. And therefore, as it moves through the deflection, there's no 1/2 involved. It was this big when he started. It was this big halfway down. It was that big when he quit. No 1/2. New beam. Here's a beam, and I'm going to put, it's the same beam, I'm going to put P sub C on there first. It is going to cause the beam to deflect. It will cause, underneath the load, some deflection at C because somebody put a load at C. And it will cause some deflection, delta at B, because someone is tinkering around with a force at C. Conduit. How much work is involved on that beam? Load times the distance is correct. I'm not sure he's going to give me the right answer, but the integral of the load times the distance is the correct answer. What was the load when you started? What was the load when you finished? What is the average load? And so you're going to multiply the average load times the total deflection moved? All right. Is equal to 0 plus P sub C divided by 2 times the deflection at B, because somebody's been tinkering with a load over at C. That's the deflection at B. In other words, we say where the deflection is with the first subscript. The second subscript will say who caused it, guy over here. Now then I'm going to add a load. This one will still be there, and it's still deflected just as badly as it was. The only thing I'm going to show you now is just the new added deflections. The new added deflections are due to someone loaded at point B, thereby causing a deflection at B because someone has got a force at B. And right here there is a deflection at C because someone's pushing on the beam at B. Baker, give me the work involved in this situation. 0 plus P sub B divided by 2. She's going to take the average force multiplied times. What was the delta again? Delta BP. Well, it's the deflection at B because of a load at B. So it's times delta sub BB. Okay? Delta sub BB. Plus, any more work involved? Johnson? Johnson show up today? No Johnsons? Galvin? Who's sitting next to you there? Your brother? I don't have anybody sitting next to Galvin on the roll sheet here. But that's okay. Oh, you moved? Well, I don't know. Tunnell is absent today. I already put a big old absent for him. Galvin? More work? What did he say? No, thank you. More work? Sorry, maybe Tunnel was listening. Tunnel? Any more work in this case here?
P sub C times delta C.
Okay, you had the P sub C force on there full blast to begin with. You had the full P sub C when you ended, so there's no 1/2, plus P sub C multiplied times the deflection at C due to a unit load at B. Would you agree that both cases are the same? When all is said and done, the amount of energy stored putting P and then at B and then at C bound to be the same amount of work done on the beam, energy stored in the beam, as putting the load at C first and then the load at B. So I'm going to tell you that P, B, delta B, B over 2 plus P sub C, delta C, C over 2 plus P sub B, delta B, C, sum of all these numbers is equal to P sub C, delta B, C over 2 plus P sub B. If I make a mistake, let me know because it won't cancel in a minute. Times delta BB over 2 plus P sub C delta CB. But P sub B delta BB is on both sides of the equation, and P sub B, thank you. Which one's wrong? All right. First off, let me see here. This is wrong. P sub C delta CC. Thank you, thank you. Whoever told me that's what that was, why didn't you get after me when I didn't write down your number? So that's the first term. P sub CC. Your comment? A little louder so we can all hear it. Go ahead. Everybody point to whoever was making the comment. Oh, they'll give you up in a heartbeat. Yes, ma'am.
So is PC still existing across the country?
Yes.
Ignore it?
No, I didn't ignore it. See, what I did, I'm sorry?
It's just not being applied at that point.
All right, here's what happens. At this point, P sub B starts at 0 and goes to a maximum number, causing these two deflections. Okay? And it causes some work. All right? Next, we're going to leave him here, just going to sit him there, and we're going to now go get another that's a car. We're now going to go get another car, and we're going to gently rest it on the beam. I must not be answering her question because she's not even listening to the answer. You understand? How did that happen? I didn't finish my explanation. Okay.
So,
Yes, sir.
can you pull it down a little bit? On
Yes,
the
sir.
same comment we're talking about, is delta BC and delta CC there both only due to the force at C?
That is correct. In other words, it's already deflected like this, but now I'd like to show you what this guy by himself did to the beam, even though this guy is there. So, strictly speaking, I can go get the load at C. I can put the load at C. I can show you an additional deflection.
So
And I can,
Is the work on the side, is that only due to the force at C, or is that due to both the forces?
this one right here is any work that got done to the beam. So that's total work. All right, so now back when we were seeing what terms, yes ma'am.
Okay, I understand the displacement due to the existing load, but on both the second pictures, why is there an inconsistency with how you label the existing?
Well, because it's probably something I did wrong. Let me look at, you're talking about the load at C.
Right, you showed both of them on the first part, and then on the other one.
I'm sorry, but I can't begin to understand what those words mean. You come up here and point.
Where your
which-
finger is, where your
This one right here,
Yes, that one I understand. And then
the second set.
yes.
All right, let me see what I got wrong here. Here's the load at C. It caused a deflection at C because you were messing around with the force at C. This is the deflection at B because you were messing around with the force at C. Now, this one is at B. You put the load at B, so that's the deflection caused at B because you were putting a force at B. And this is the deflection at point C because you were putting a force at B.
No, but you're not showing PC on that one.
I'm sorry, what?
You're not showing PC on that one still? Why?
Well, it's there. I don't know how hard to show it.
Okay.
All right.
Thank you.
No, I don't think that's going to make it. If I can't get that across, we'll do it this way. Because it's okay. Here is the force at B, and here's how it really deflects. And this thing right here is the deflection at B because of a force at B. And this thing right here is the deflection at B, at C because of a force at B. Now the book shows it this way. If you understand it, okay. This will work. The next thing I'm going to do, let me put the force underneath it, okay? On top of this, here's how much work we have in the structure right now. The total work we have so far is equal to P sub B times delta BB. That force started at 0 and went to P sub B, so it's the average force. That's all the work that anybody did to it. Now the car is there. It's sitting, it's been put there slowly and gently by a crane. Next, I'm going to go get another car, and I'm going to set it at point B. Here is that car. That force is at C. That causes this beam to do this. I'm not sure it's as easy to show or not. It's up to you. This number right here, that is the deflection at point C because you came in, put a load at C. And this deflection right here is the deflection that you caused at B because you put a car at C. From the position 1 to the position 2, you did some work on the beam. The amount of work you did on the beam, first let's talk about the car at C. When you started letting the car down with a crane very gently, it had no force on it, none at all, no force, not even a little bit, no force, none at all. Wheeler, how much force? Well, I don't know, you're in that seat. You're the one sleeping. No? Okay. Why is drool coming out of your mouth? Plus, When this started at 0 and went to full blast, you put an average force of P sub C over 2. And the deflection through which it traveled was the deflection at C because you put a force at C. And that's all the work involved. And then somebody says, wait. There's another car was sitting over here that you didn't even know about. And I look over, indeed, it's a Cadillac. And I say, well, I hope it didn't move because that would have caused work on a beam, which I haven't accounted for. He says, it moved. I said, did it move a lot? He says, yeah, it moved that much. The force at the beginning of this study from 1 to 2, was P due to a Buick. And at the end, it was still P due to a Buick. And therefore, it's P sub B, full blast, for delta BC. Now, I'm not going to bother doing the other one. If you see that one, you should be able to do the other one. Here's how much work is involved. P sub B, delta BB over 2. There's P sub B, delta BB over 2. Here's P sub C, delta CC over 2. There's P sub C, delta CC over 2. Here's P sub B, delta BC. There's P sub C, P sub B, delta BC. There's all three terms. Get them any way you want to. So we're at that stage where I couldn't cancel those terms out because I had one of the coefficients misnamed. PB delta BB is on both sides. I don't know what it is, but it cancels. PC delta CC over 2 on both sides, and it cancels. That says that the force that you put on the structure at B times how much deflection is caused under that load because you put another load someplace else is equal to the load at that other place times the deflection under the C load because you put a load at B. It's called the Maxwell-Beatty law of reciprocal deflection. And it is truly very useful, very handy. So for example, if I told you that it works for any structure, and if I told you that you put a 100 kip load right here, and it deflected the beam like that, however it deflects it, and it deflected it this much, this would be 100 kips, and this is some deflection. And then I have another structure, looks the same. I don't know why I say it's another structure. I have another one, but it is the same. And I put a 60 kip load here, and it causes the structure to look like that. And I call this guy the load at B. And I call this the deflection at B because you put a load at C. And I call this P sub C. And I call this the deflection. This is the deflection at B because you put a load at C. This is the deflection at C. I don't need that one. Times the deflection at C because you put a load at B. You got to think about it a minute. Here's the equation. P sub B, this guy right here, times how much deflection you get at B because you put a load at C has to equal to the load at C times the deflection caused at that point in that direction, because you put a load at B. What it really does is it lets you cut half of your number work down when you calculate forces in statically indeterminate structures. All right, in a minute I'll show you one of those where you can get some use out of that. Let's say I have a structure and it is loaded two kips per foot, 20 feet, 10 feet, 30 feet. Point A, point B, point C, point D. If I asked you to draw a shear in a moment diagram for me, what would you tell me? Who said bug off? And he says, I can't do that. And I say, well, let me show you how. And I would look at it and I'd say, well, you know, I can't do that either. And the reason is you have three equations of statics, and you have 1, 2, 3, 4, 5 unknown reactions. You have an A horizontal, you have an A vertical, you have a B vertical, you have a C vertical, and you have a D vertical. Now, well, you may say you think some of those arrowheads are in the wrong direction. Some of them are, but they're not all in the wrong direction, as a matter of fact. Some of them are in the right direction. And I'm not sure if either of us know which is which, and so I'm just going to assume that they're all in a direction of your choice, perhaps down. Which way are they? Alan? Never mind. Hunter? Sorry, sometimes when I shoot, I don't get the right guy. I'm looking for somebody with his hat on backwards. Hunter? Never mind. I don't know how you guys learn this stuff. I mean, I swear, you must wait till you get home and ask Mom. That's all I can imagine. All right, so I am going to take off 2 supports because that's the only way I know to get it down where there's enough unknowns that I can just get a start on it. Once I get a start on it, I can beat it to death with a stick. But until then, I'm just not going anywhere. So here is what I will call the primary structure. Yeah, I fully understand. It's a mess. It's not right. It doesn't have, the old structure was supposed to do this and come through that point and then probably come through that point, and then it had to come back. I know mine doesn't do that at all, but that's what I'm going to start with. I'm going to take my statically indeterminate structure and turn it into what they call a primary structure, which is one that has enough redundance removed such that I can get a shear in a moment diagram, so I can get all the reactions, and then I'll get in there and I'll fix it. I'll put some forces at these places to make these displacements go away. Here is the load. That is 2 kips per foot. And the deflections will sadly look like that. And I will be able to draw a shear in a moment diagram. I probably won't even need a shear diagram, but I'll be able to draw a moment diagram because you and I are getting ready to integral M due to the Q loads, M due to the P loads, dx over EI, and the shear doesn't show up in there. If you had a short, squatty, thin beam, shear deflections would be important, wouldn't they? Open a good north. but he didn't even hear his name called. What do you two guys have going on over there? Man, she must be really good looking to talk about her a whole class period. This is the deflection at B. Let's call it the deflection B0 due to the real loads. That is sad. This is the deflection at C0 due to the real loads. Here's a moment diagram for this case. The moment on the left end is 0. The reaction, you got a calculator there? Or is that a phone for texting? Oh, okay. Here we go. I get some help from people who aren't busy doing anything else useful. Hunter, you got a calculator?
Yes, sir.
Good. Give me the following number. 2 times 20 times 30, 40, 50 equals, and divide that number by 60. 33 and a third, thank you. So this reaction is minus 33.33 kips. Take that same number, Hunter, and I'll tell you what, I'm going to just go ahead and sum moments again. 2 times 20 times 10 divided by 60. 20/3. Don't you have something that's 6 2/3? 6.67 kips of force. All right? Now I want you to give me the following number. I want you to tell me 33.33 times 10 minus 2 times 10 times 5. 233.33, okay, thank you. Hang on. I'll be using you all class here. Now then, I would like for you to multiply 33.33 times 20.
666.
From that, subtract 2 times 20 times 10. Morning, Mr. Gitman. 266.67. Let me admit to you, I have no idea where the maximum is. Okay, so I know what the moment diagram looks like. Now then, Alan, Hunter, I forget who I'm working with there, Hunter. I want 33.33 times 30. And from that, I want you to subtract 2 times 20 times 20. 200. And then I want you to multiply 6.67 times 30. Okay, that's good. That means the diagram closes. There's the moment diagram drawn on the compression side. Side of your choice, I'm going to draw it on the compression side. That would be called M0. And probably also called M sub P, because it's due to the real loads, the P loads. Now then, in order to find the deflection at B0, let me start over. I need to find the deflection at B0 so that I can later on get rid of it. I can make it go away. Pick somebody at random here. Open north. What would I do? How could I solve for the deflection at B0? And I'll give you a hint. The answer is put a unit load at B. That's correct. And that would give me M sub due to the Q loads. And then I could integrate M sub P, M sub Q dx over EI. That would give me the answer for the deflection at delta B0. Here is the beam. Here are the supports. You know, I don't know if I'm going to be able to live with those reactions there shown down. It just, let me go ahead and pick them up as up. Let me pick the other two as down, because I'm not constantly trying to draw a shear and a moment diagram with them and get rid of the minus sign. Because I'm getting ready to assume that this answer is indeed down, the deflection is indeed down, and therefore I'm going to put the unit load down. It causes some deflections. Bustamante. I know you figured that I was going to pick on those two guys mercifully for the rest of the class, so you were in the clear, but not the case. This right here, let's give it it's a little, due to a little load, let's call it a little deflection. That deflection would have what two subscripts? Looking at the original case, hint, hint, it would be the deflection at B due to some jerk put a load where? Where did he put the load? That's correct. That fully defines that deflection's got a good name for it. This deflection right here would be the deflection Kruger. That's correct. This is the deflection at C because somebody was tinkering at B. I don't know if we'll ever use that or not, but there it is. Now, while I'm at it, let me go ahead and this is the deflected shape. This is the moment diagram that goes with it. This is the deflected shape. Here's the moment diagram that goes with it. Drawn on the compression side. Hunter, 1 times 20 divided by 60. 30. Thank you. 0.333. And then without a doubt, this one is 0.666. 667. Here's the moment diagram. This is nothing but a force on a piece of steel. There's the piece of steel. There's the piece of steel. That force times this distance, 20 feet, should give me the moment. 0.667 times 2, 20. 2 times that would be 1.33. And another one. What's 20 times 0.667? I guess that is 13.33. And what is 0.333 times 30? Hunter? 10. And what is 0.333 times 40? Is it? Okay. That's the moment diagram due to a Q load, 1 kip big, acting on the same structures we had before. Now I have a moment diagram for the M sub P, and I have a moment diagram for M sub Q. And so all I got to do is integral MM dx over EI, or I can use volume integrals. Shouldn't be that hard to solve for the equation for any of these. The equation for this one ought to just be 0.667x. And that ought to be good all the way to there. And the equation for this one ought to be 0.333 times x. And it ought to be good. Nothing new changes, so it ought to be good all the way to there. And the equation for this one ought to be 6.67x. And you have two ranges. The only one that I'm not sure I've really shown you that I can do would be this one right here. Here's what I would do. I would cut through the beam at a point X. Here's what the beam would look like. I cut off a chunk X. It has 33.33 on the end. It has a uniform load down of 2. Here is the bending moment. That is M sub Q, no, that's M sub P, should equal to 33.33 times X minus 2 times X times X over 2. So we ought to be able to integrate MM dx over EI. But I like volume integrals. And I can do that integration. It's just multiply that equation times this equation and integrate between 0 and 20 and do the same thing for this equation times that equation from 0, actually it goes all the way out to 40. But here's what I'm saying. Integral of m dx over EI is equal to the integral of this guy his height is 233.33 and his height, I think it's kind of interesting how it doesn't matter what the peak is. The truth is, if you give me the height of any 2 points on a parabola, I can tell you what the equation of that parabola is. It's fixed. And if you give me the one in the middle in this one, it's even easier to do. And this height is 266.67. It is supposed to be integrated with this 20-foot thing right here. Plus, you're supposed to be integrating this equation with this equation. That's a triangle, 266.67, combined with another triangle, 13.33. Ta-da! Hey? Thank you. Who brought their volume integrals with them? Look at this. You got them? All right. What is the result of integrating a parabola with a triangle?
Which one would you go with for the parabola one on the volume integral sheet?
Hang on. Had a whole bunch of them left over from yesterday that I saved for sale for today. It doesn't matter, I don't think. But just out of, self-preservation, I'd probably pick this parabola with this triangle. So I would pick this one. Oops, I'd pick that one right there. My guess is you're going to get the same answer if you do the other one. Only thing is the A's and the B's and C's will change. Anyone like to buy one of these off of me? Anybody not have one? If you didn't even get one last time, you deserve one more than the other guy. You will have to walk up here and get it, because if you think I'm going to deliver it, you're nuts. What did he say? Get me one too? Tell him to go away. He lost his. I'm running out.
Thank you.
Certainly. All right. Therefore, LA onto 2D plus E, LA onto 2D plus E divided by 6. I highly recommend then you go label these numbers here. It's really easy to get them messed up. This guy is E. The mid-ordinate value is D dog. So D. And the left ordinate, this one here, is C. So C will be 0. Look at that. C doesn't even show up in the equation, does it? I guess he knew if it's, no, he knows it's going to go through 0. All right. And on the triangle, that's a A. So this guy is A. Plus 2 triangles facing the same way. That's this one and this one, or this one and that one. It is the volume of an eraser cut diagonally when you laid it on the table, and then you face it up, and again you cut it diagonally so that one end is very sharp, comes to a point, LAC over 3. And you got to be careful. You just have no idea how many people will be taking this class next semester, because L is L is L. It said L, so I stuck L in there. And no more than do you stick 20 feet in both places because you figure L is L. It's not. It's tuned to that, and that one's tuned to that. So it's equal to, the length is 20 times A is 13.33. And times 2 times D is 233.33. Plus E is 266.67 divided by 6, plus, don't forget the EI. Volumes don't know anything about EIs. Boy, it's got to be a boring lecture, doesn't it? When they walk out in the middle. Plus L times A times C divided by 3EI. That is the deflection of that structure at point B due to the real loads. Because it was due to real loads, I went ahead and gave it a big delta. Your choice. Yes, sir.
What about the reaction at C? That doesn't affect this at all?
The reaction at C, you mean way over here? Yes, it does. But you've lied. You lied like a dog. These numbers here have been removed. And the question was, how badly did this thing move down when these were not around? They had been taken out of the structure. That's what we're trying to solve for right now. All right, now then, one of the things I'm going to have to be able to solve for is B vertical, and B vertical is going to have to do something to help me get rid of this delta B0. So probably it's going to turn around and go the other way. I won't worry about that. It'll come out with a minus sign if it's guessed incorrectly. But when you put it on there, it's also going to move the beam at point C. And therefore, I really need to know how much deflection it's going to cause. Let's just do to a one-kip force first. Just the deflection at B due to B. If I ask you for the deflection at point B due to a real unit load at B, incidentally, I'll make that the right size by multiplying whatever you give me here times B vertical. How would you get the deflection at B because someone put a force at B? That's the same question I asked you a minute ago. Somebody finally coughed it up. I think I gave him a hint. How? Put a unit load. Excellent. Put it where? At B. That's exactly what I would do. It doesn't make any difference what the real load is. I would take a unit load and I would put it at B. So to find the deflection at B, and let me write it out, make sure nobody has any questions. To find the deflection at B due to a real B vertical load, I'm not going to go there just yet. I'm just going to say due to a unit load. When you give me the answer, I'll multiply it times B vertical to get the whole thing. Due to a unit load at B, which is called delta BB. Well, first I have to have an M sub Q. You told me how to get it. You told me to put a unit load at B. And then I'm supposed to put a real load on the structure. And I'll admit that the real load is B vertical, but as I said, right now I just want how much is due to a unit load, and I'll multiply your answer times B vertical, and therefore here's the real load. And therefore, well, that ought to be pretty easy. Here's the moment diagram that goes with this one. Summing moments about this point, 1 times 40 divided by 60. That'd be 2/3, right? 0.667 kips. And 0.333. What time is this class over? Right now, you lie. 3:35. Give me 10 minutes before class ends. You got to watch? Got to watch? Can you? No? You're no help. You got a phone? Text me. That'll work. Give me 10 minutes so I can give you back the quizzes. 0.333. Here's the unit load. Here is the moment due to the phony load, the dummy load, the virtual load, the unit load, the one kip load. Looks like that. Force times distance, 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 force times distance. 0.667 times 20. Seemed like we just did that. Did we just do that? Yeah. We just got that one. Heck, look at this. We already got that one. We needed it to get this real load deformation. I already got that moment diagram. It's up here at 13.33. And of course, the real load one looks exactly the same. And therefore, the deflection at B due to a unit load at B is equal to the integral of this plus this. Now, I'm not trying to go so fast you don't understand, but all we're going to do is integrate this equation multiplied times that equation, and we're going to integrate that equation multiplied times that equation. And this particular length is 20. And this particular length is 40. And here's the moment diagram. And if you got the volume integrals, all you got to do is add them up. So I'm going to tell you known. I know that number. Now then, while you are tinkering around putting your force at B vertical, you're also going to be influencing my deflection at C. And I'm going to have to know how much you move the beam when you put your load over here. So I'm going to go ahead and calculate delta CB. To calculate delta CB, I hope you know the words, is the deflection at C because you put a reaction at B. I need a moment diagram, Q, and I need a moment diagram due to the real loads. The real load is, yes, I know, it's R sub B. Let me just put a 1 on there and I'll multiply it out later. And where would you put the unit load? Skeleton? On this one right here. No, I'm sorry, I've got the unit load. That's not good. That isn't what I want. I want to know to find the deflection at C, that's the deflection right here, due to a load at B. And I'm not really there yet. Yeah, that's right, C is down the road. I am there. So the real load, here's your load at B. There's your R sub B, which you have kindly let me go ahead and knock it down just to a 1, and I'll multiply it times R sub B later. That's the real load. Now, skeleton, where do you want to put the unit load? Loud enough so everybody can hear you, including me? C, Charlie, is correct. You put the load at C.
10 minutes left.
You lie. Sure, you lie. I know you lie. You always lie.
Oh, no, they're serious.
No, I don't believe you either now. I'll give you your quizzes back next time.
That's good. We'll ruin my weekend.
All right, we'll take this up here next time. Oh, I know it was so good. You just hate to quit.